So, someone had asked me to go over molecular orbital theory for benzene. We can totally do that. I'll give you guys like a minute to let me know what else you would like to cover. What kind of stuff do you want to work on today? Any specific questions? Let me know. And while you guys tell me that, I'm going to start sharing my screen. Please let me know that you guys can see it, right? Sweet, okay. And then someone asked, do you need to know the different names of benzene rings? Could you please clarify what you mean by that? Like what different kinds of benzene rings? Also, thank you for confirming that you can see it. Oh, okay, like naphthalene and stuff. So you don't really have to know those for this chapter. For next chapter, I'm going to give you guys a couple of common names for benzenes with different substituents and stuff, and those you will have to know, but off the top of my head, I don't remember which ones are important to know. I don't believe naphthalene is one that you have to know, but since you're curious, that's just like a benzene ring, like a double benzene ring. As far as ortho, meta, para, that kind of stuff goes, we will be learning about that next chapter, and we can go over it really quick at the end of this if you would like, but we're definitely going to learn about that next chapter. And stuff like toluene or aniline, that stuff for sure is the common names that you guys have to know. That will definitely be in chapter 15. And you will have to know like the common name and the real name. So like, for example, since one of you guys brought it up, this is an ugly benzene ring, but don't mind that. So this is a benzene with a methyl group, and the common name for that is toluene. And it's also called methyl benzene. But again, we'll go over all that in chapter 15. Oh, really? His lecture for chapter 14 went over that? Dr. West likes to jump around, is what I've noticed. But since he is going over that in his lectures, I'll go ahead and make sure I send you guys the chapter 15 handout today so that you're not like lost and you have something to reference back to. Sound good? You're very welcome. Okay, so unless anyone has any like huge objections, let's go ahead. I don't know why my screen is being wild. And do molecular orbital theory. So I'm going to draw out our benzene ring. And then we are also going to do cyclobutene, but we'll focus on benzene first. And since someone actually mentioned it, what is the IUPAC name for benzene? What do you guys think? Yes, exactly. Someone said it in the chat. So it is 1, 3, 5, cyclo, hexa, triene. And if you just know it as cyclohexatriene, that is also good enough. But to be most correct, you should include the 1, 3, 5 on there. And so this molecular orbital theory, like way of looking at it for benzene, is actually kind of strange. And the reason I say that is because in the last chapter, every one of the carbons had a p orbital, and then we like did all the energy levels and all the stuff like that. this is kind of strange because the energy levels are not going to just be one after another like we did. I don't know how to explain it in like simple terms, but like, you know how we did it where it was like 1p orbital was the bottom one, and then we add a node, and then it's one energy level higher, and then on and on. Okay, good. So in this case, instead, we're going to take each one of these carbons, and in that spot, we're going to put an energy level. So it's going to look something like this. And so 6 carbons would equal 2, 4, 6 energy levels. And there's a couple things we have to take note of before we go on any further. So the first thing is we have something called degenerate orbitals. And all this means is when we have multiple energy levels, or multiple orbitals, in the same energy level. So this is a set of degenerate orbitals, and that is a set of degenerate orbitals. Because again, all that means is multiple orbitals on the same energy level. And when we number these, we're going to call it pi 1, pi 2, pi 3, 4, 5, and 6. And no, it didn't matter if I went 2, 3, or the other way around. It could have been 1, 2, 3, 4, 5, as long as you know that 1 will be by itself on the bottom, and then 2, 3, and then 4, 5, and then 6 is by itself at the top. And so another thing that we know from chapter 13 when we did molecular orbital theory is that the number of bonding and anti-bonding orbitals has to match, and it has to be the same. For degenerate orbitals, it's the same rule. It's just a little bit of a more strict rule, I guess, where multiple orbitals on the same energy level have to be the same. So pi 4 cannot be bonding, and then pi 5 is antibonding. So now instead of orbitals, I'm going to say energy levels. So we have to have the same number of bonding and antibonding energy levels. You can think about it the same way that we did before. It's just I find that it makes more sense to students if they think about it as energy levels here. And so kind of what I mean by that is we're going to split this in half. So I'm going to do a dotted line here, right? Because we have 2 energy levels on the bottom, 2 energy levels on the top. So pi 1, 2, and 3 are all going to be bonding, and pi 4, 5, and 6 are all going to be anti-bonding. So let me draw that little star in here. And then on the side, I'm going to say bonding will be pi 1 through 3. And anti-bonding will be pi 4 through 6. Any questions so far? I know it's kind of a lot. Or is it kind of okay? It's okay. All right, good. So why were pi 1, 2, and 3 bonding? And we can say again, the easiest way to do it is just to cut your diagram in half, and everything below the line will be bonding, and anything above the line will be anti-bonding. But the more scientific explanation has to do with the stability of the orbitals. So pi 1, 2, and 3 are at a lower energy level, so they're going to be housing the electrons, and they are going to be what's doing the bonding. And then the anti-bonding orbitals are going to be higher energy, so they're not going to house electrons, and they're just going to be used in reaction mechanisms, but that's too much in detail. I don't want to confuse anyone. Was that a sufficient answer, you think? Okay, cool. So now that we have this basic idea of what the energy diagram looks like, we're actually going to start filling it in. And so in order to do that, I'm just going to go ahead and erase this green line to make it a little bit less confusing. And now I would like you guys to tell me how many pi electrons are in this. Six, exactly, because 1, 2, 3, 4, 5, 6. Or you can think about it, 2 from each double bond. And so now another thing about degenerate orbitals is as you are filling them in, you're no longer finishing one orbital and then moving on to the next. You actually have to go by energy level. So 1, 2, we finish the first energy level. When we go to the second one, it will be 3, 4, and then we go back 5, 6. In this case, it doesn't really matter if you knew that, and you just filled up 2 and then went on to 3 because it evens out. But for the rest of the examples, you will for sure have to know that you would have to do 1, 1, 2, 2. All right, so at this point, we can figure out which one is the HOMO and which one is the LUMO. So which one is the highest occupied molecular orbital? Pi 3, exactly. So I'm actually going to move this over a little bit because it's starting to look kind of messy. But Pi 3 will be the HOMO. And so which one will be the LUMO, the lowest unoccupied molecular orbital? Pi 4, exactly. So this is going to be our finished diagram for the ground state. So I gave you guys a table up here. So we're just going to go through and fill that out. I will ask you all of these questions, but I'll go back to the diagram so you guys can see it while we talk about it. So I didn't explicitly write this, but how many atomic orbitals do we have? Atomic p orbitals, I should say. 6, exactly. And that translates to how many molecular orbitals? 6 again, exactly. And so we know that there's 6 of each. In this class, that'll always be the case. And so how many bonding orbitals do we have? 3, sweet. How many antibonding? And do we have any non-bonding orbitals? No, perfect, okay. So then how many bonding electrons do we have? And then someone asked, this is because we have an even number of carbons. Yes, but more specifically because you have an even number of orbitals or energy levels. But since it's fully conjugated, yes, you can also think of it as an even number of carbons. But yes, exactly. So there are 6 bonding electrons, and the reason there are 6 is because, remember, all 3 of these are bonding orbitals, so all 6 of these electrons will be considered to be in bonding orbitals. And so how many anti-bonding electrons are there? 0, exactly, because we're in the ground state, there's nothing in antibonding. And so how many electrons are in the HOMO? 2, perfect. And then how many are there in the LUMO? 0. Perfect. Okay. And then let me just double check, but I think we went over all the questions. Yes, sweet. Okay, so any questions about the ground state? Sorry, my screen is moving around so much. Any questions about benzene in the ground state? Nope. Okay, cool. So then one other thing I can ask you that's new to this chapter is how many pairs of degenerate orbitals do we have? Someone's okay, cool. 2, we have 2 pairs of degenerate orbitals. And so if I asked you how many degenerate orbitals are there, what would the answer be? Ooh, we got a split. Okay, the answer would be 4. And the reason I say this is because people get tricked all the time. He could either ask you how many pairs are there, or he could just ask you how many orbitals are there. And if he asks you how many pairs, there's 2, because there's like these 2 sets, pi 2 and 3, and then 4 and 5. But 2, 3, 4, and 5 are all considered degenerate orbitals. So if he asks you for pairs, it would be 2. If he asks you for how many degenerate orbitals there are, the answer would be 4. And then he could also ask you how many electrons are there in degenerate orbitals. 4, exactly. Perfect. Alrighty. So now if we go to the excited state, let me just specify that that's ground. And again, we know that most things don't change between the ground and excited state. So I'm going to go ahead and duplicate this and just do excited. The only thing that's going to change is our electron placement. So I'm going to go ahead and zoom in here. And so we know that the most favorable movement of electrons will be from where to where. And then I see the question in the chat. I will answer that once we do this one thing. So yes, the most favorable energy transfer is from the HOMO to the LUMO, aka pi 3 to pi 4. So the electrons in pi 1 and pi 2 stay the same, but the second electron from pi 3 will jump up here to pi 4. So now we're going to answer all of those questions again. So how many bonding electrons are there? 5. Ooh, we got a couple different answers. Okay, so let's remember that the naming and everything did not change. So these 3 are still bonding orbitals, and these are still antibonding, right? And so all of these electrons are going to count as bonding electrons. So we're only going to subtract by 1 because 1 went up to the antibonding. So we are going to have 5 bonding electrons and 1 antibonding electron. And so now how many electrons are in the HOMO? 1, perfect. And then how many are in the LUMO? 1, exactly. So let's go up to the table. And I'm sorry for moving it around so much, but we knew that there are 6, 6, and 6. And we know that that doesn't change. So 6, 6, 6. Oops. Anyway, how many bonding molecular orbitals are there? We said 3. How many antibonding? We said 3. Again, this doesn't change. And I'm going to go ahead and put 0 for both non-bonding categories because we know that there are no non-bonding for this. So the thing that changes is the electrons. So in the ground state, we had 6 bonding electrons and 0 antibonding. And in the HOMO, we had 2. In the LUMO, we had 0. And we know that in the excited state, we lose 1 bonding electron and gain 1 antibonding. So then we will end up with 1 in the HOMO, 1 in the LUMO. That doesn't look like a 1. 1 in the HOMO and 1 in the LUMO. And so I'll leave this up while I answer a question that I had in the chat, which was essentially degenerate orbitals are energy levels with more than 1 molecular orbital. So yes, essentially, I would say to kind of flip around your wording though, because a degenerate orbital is just multiple orbitals on the same energy level. A degenerate energy level would be one that has multiple orbitals. So yes, the concept was right. Just kind of flip around your wording a little bit. Make sense? Okay, cool. So any questions about benzene in the excited or ground state? That was supposed to be more graceful. I'm sorry you had to witness that. Okay, so if not, let's go ahead and do the 1,3-cyclobutadiene. I'm going to scroll down again so we can draw it. Okay, that's not what I wanted. So we call this 1,3-cyclobutadiene. And I'm going to ask you, is this aromatic, not aromatic, or anti-aromatic? This one is actually anti-aromatic. So the reason for that is it is cyclic, planar, and fully conjugated, but we have 1, 2, 3, 4 pi electrons. So what rule does that follow? Is it Huckel's rule or the other one? The other one, 4n, exactly. Cool. So now this is going to follow the same idea. It's just going to be slightly different. And so I don't know who came up with this, but essentially all you're going to do is take this and make it so that it is sideways like so. So it's kind of like a diamond. And we're going to do the same thing where we just put an energy level for every point. And my diamond's looking kind of rough, but essentially the energy levels would look like this. Right? And when we go to name them again, or number them rather, we know it's going to be pi 1, pi 2, pi 3, and pi 4. And then someone asked, can I explain what an energy level is? Yes, exactly. The blow up. Sorry. Yes, so that's one of those things that they never really explain to you. They just kind of say it and expect you to know. So essentially, an energy level is each one of these blocks where we have electrons. So in this one, it's a little bit weird to draw the orbitals and everything. But if we go back to chapter 13, you know how we drew these nodes and everything? Well, essentially, an energy level is just essentially telling us about the nodes. So the bottom energy level doesn't have any nodes. So it's super stable, very low energy. And then as we go up, we have one node. So this area has a little bit more or higher energy, I should say, and then higher energy and higher energy. So energy is one way to think about it. Another way to think about it is kind of, I want to say this in a not weird way. So we can almost think about an energy level as the likelihood that there is electron density in a certain place. So at the bottom level, there's equal electron density everywhere. Versus here, there's an unequal distribution of electron density, and then it becomes more and more unequal as you go higher. That's a really weird, like, not weird as an incorrect, because that's like the correct way of thinking about it, but it's weird if you haven't had more experience in chemistry. I don't know. I feel like that explanation. Okay, great. Anyways, moving on. They always tell us, like, don't tell your students anything, like, outside of the scope of the class. But you guys are always so curious that I'm kind of like, I want to tell you, but I don't want to confuse you. But, yeah, anyway. So, this set of orbitals right here are going to be degenerates. And that is because they are on the same energy level again. And now we have a problem because we're going to cut this diagram in half in order to figure out whether, like, what's bonding, what's antibonding, whatever. So if we cut this in half, we actually cut through one energy level. So what do you think is going to happen? Any ideas? Perfect. So, yes, for sure. One is going to be bonding. And since 4 is kind of like the opposite, it kind of corresponds to it. 4 is going to be antibonding. And so that would mean we have non-bonding here. Because now you still have an even number of orbitals, but you have an odd number of energy levels. So this energy level in the middle has to be non-bonding. So, sorry for making it sloppy. So pi 2 and pi 3 both have to be non-bonding. And I know you're probably thinking, well, we still have an even number, so why couldn't pi 1 and 2 be bonding and 3 and 4 be antibonding, right? But remember what I said for benzene, you can't cut an energy level in half. So degenerate orbitals have to have the same status, so either bonding, antibonding, or non-bonding. Does that sort of kind of make sense? Yes? Okay, cool. And yes, I could definitely repeat that. So the ones in the middle have to be non-bonding because now we're going to look at even versus odd energy levels, not orbitals. So since we have an odd number of energy levels, the one in the middle has to be non-bonding because we cannot cut an energy level in half. So all of the degenerate orbitals on one energy level must be the same. So they either all have to be bonding, all have to be non-bonding, or all have to be antibonding. So now let's go ahead and fill in our electrons, and you guys already told me that we have 4 of them. So first energy, the energy level doesn't have any problems. Bam. But then when we go to the second one, it's very, very important that you do 1, 2. Uh-oh. Now, what is the biggest difference between this diagram and the one we drew for benzene? What sticks out to you guys? Yes, exactly. So the energy levels are not full. That's really, really crappy. So these non-bonding orbitals are half full. And so this is exactly why antibonding is so sucky. Because Half-filled energy levels are super, super, super unstable. We do not want that. Sort of kind of makes sense? Cool. And then off-topic question, but does this happen in straight chains? It is not likely because this is one of those things that come from aromaticity. I'm not going to give you a hard no because I'm not actually sure, but I'm 99% sure. But yeah, for sure, don't worry about it. And also another kind of like hint, as far as molecular orbital theory goes for chapter 14, you only need to know these two examples. He's never asked about anything else. So the last thing is our HOMO and LUMO. So you guys tell me, which one do you think is the HOMO and which one do you think is the LUMO? Yes. So pi 3 is the HOMO and pi 4 is the LUMO. And this one, people tend to get really confused. You guys seem to have gotten it because, like, most people answered. But people get confused because each of these is half full. But the HOMO does not have to be completely full as long as there is one electron in it that can be considered the HOMO. So when we go to the excited state, I really don't want to redraw this, so I'm going to copy and paste it again. The only thing that is going to change is the electron from pi 3 will jump up to pi 4. Bam. So, ground. Excited. And then someone asked, why couldn't pi 2 be the HOMO if it's the same energy level? That's a great question. So it's one of those things that I think is just a convention kind of thing. Because, like, as you're saying, they are degenerate, so they're on the same energy level. And I think it's more just... That's a good question. I don't exactly know the scientific answer. I just know that when we're writing it, just that's how it goes because you fill up 2 and then 3. It probably has to do with quantum numbers and stuff. So I would just say don't worry about it. Don't ever apologize for being curious and asking questions. I love questions. I just feel bad sometimes when I can't answer them. Okay, so I'm going to scroll up a little bit and zoom out a tad so that we can answer these questions. So how many atomic and molecular orbitals do we have? 4, exactly. And that doesn't change. And how many pi electrons do we have? 4 again, sweet. So how many bonding molecular orbitals do we have? 1, cool. And antibonding? 1. And non-bonding? 2, exactly. And then, so in the ground state, how many bonding electrons do we have? Ooh, okay. So I got 2 different answers. Remember, okay, never mind. So yes, we would have 2 because remember in this case, only the bottommost energy level is bonding. So how many anti-bonding do we have? 0, pretty much as always. And then how many non-bonding? 2, perfect. So how many electrons in the HOMO? Only 1, exactly. And we know the LUMO has 0. So in the excited state, how many bonding electrons do we have? Still 2, exactly, because we're not touching the bonding. How many anti-bonding do we have? 1, exactly. And now non-bonding, how many? 1, cool. And then so how many electrons in the HOMO? 0. How many in the LUMO? 1, exactly. So those two just flip-flopped. And yeah, so that's pretty much it. You guys have mastered molecular orbital theory again. Actually, I lied. I'm going to ask you one more question. So how many pairs of degenerate orbitals do we have? 1. What if I asked you how many degenerate orbitals are there? 2, exactly. What is the most favorable transfer of electron? Like from what orbital to what orbital? Pi 3 to 4, exactly. I don't know why that was so hard for me to get out. So yes, the most favorable transition would be from pi 3 to pi 4. And that's pretty much it. Unless you guys have questions, that's pretty much all the stuff you have. And then someone asked why. Good question. So we're moving from the HOMO to the LUMO. That's always going to be the most favorable energy transition. So just go in and find which one is the highest occupied. That would be pi 3. And then the lowest unoccupied would be pi 4. And so that will be your most favorable transition. And then someone asked, are those the only degenerate orbital questions he could ask? Essentially, yeah. He could also ask, like, which 2 orbitals are degenerate? And then you would just say pi 2 and 3. And then I've never seen him ask this, but he could say, like, are the degenerate orbitals bonding, non-bonding, or anti-bonding? Theoretically, he could ask you that. And so, in this case, they would be non-bonding. But other than that, yeah, these kind of questions will be pretty straightforward. You are very welcome. I'm glad it makes more sense. Yay. On the last one, he gave a pentadiene. So, like, the cyclic one or just like this? Okay, so if he gave you guys this, he was, I think, just purposely trying to trick you because he also just goes over butadiene in class. So this actually would be exactly the same as the butadiene because this carbon might as well not be there because it's not like a cation or an anion or anything. So this would still have 4 energy levels, and it would have 4 pi electrons, and it would still kind of go like that. So this would be the HOMO, LUMO, and then this would be your energy transfer. I should have probably shown you an example of the pentadiene, but yeah, if he gives you something like this again, which he probably won't, but in case he does, this would just not even count. And so that's a fair question that someone just asked. Could he give you anything other than what we just went over? Theoretically, I guess he could, because every anti-aromatic will look like this, and every aromatic will look, like this. But that being said, I have never actually seen him do that. He is pretty standard because once you get into aromatic compounds, it becomes more complicated. So yeah. So cyclopentadiene would not follow the same orbital theory as this because it would not be aromatic, right? Because this would still be sp3, and so non-aromatic stuff don't count. So it only counts if it's aromatic or anti-aromatic. Exactly. So non-aromatic, we don't apply these rules. And then someone said cyclopropadiene. So a cyclopropane would look like this. So I don't think you could have a diene. Do you mean like one that looks like this or something? Okay, so something like this could have the same idea, but I don't think he would ask you about it just because it would be kind of the same because it's anti-bonding, or excuse me, it's anti-aromatic because it's still 4 electrons, and it has the same number of electrons as the butadiene. So it would essentially be the same, but the concepts behind it are different. I can check with him and ask him, but again, I've never seen him do this. But it would look the same, essentially. Okay, so yeah, I can repeat that. So for this, technically, I guess he could do, I don't think he would ask you, but I guess he kind of could because it is anti-aromatic and it still has 4 electrons, but the arrangement of the orbitals would be different. So unlike the other example where we knew how to arrange them, you can't just look at this and know how to arrange these orbitals, so it's not a fair question. So yes, one thing that we haven't done in SI yet that I think will come up on the exam is this molecule, and it's the resonance structures for this. So do you guys want to go over that real quick? Yes? Okay, cool. So essentially, he will give you this, and he'll say, how many resonance structures does this have? And so essentially what you need to know how to do is resonance in the ring. So our first structure will look like so. That looks so ugly. Okay, better. So I'll draw the changes in red. And this side is still the same. And then we are going to move these electrons like so. And now, at this point, we have pretty much changed the orientation of all of the electrons, right? Because it's flipped. And then someone asked, would you have to move the red double bond? So in the next round, yes, we will move it, but so far we haven't moved it yet. So in the next step, we will bam, bam. So it will look like so. And now we have our electrons here, here, and here. And we can move this once more here. And we end up with our negative charge on this carbon, our double bond here, and another double bond here. And our last resonance structure would just be moving these electrons up here and these back here. And I'm not going to draw another structure for that because that would just take us back to this right here. So how many resonance structures does this molecule have? Five. Yes, exactly. And if you're anything like me, you're very confused about why. Because when I learned about this, I was like, that makes absolutely no sense because, like, if you're rotating this thing, like, you get all these answers. Like, I don't know, it just made no sense to me because I was like, this is just a pentadiene, like, it's all the same. Yes, you're kind of right. So what my professor told me is, like, yeah, it's kind of the same, but when you're doing resonance, like, all you have to think about is the fact that all of these delocalize. So while these are all kind of showing you the same thing, it's just a matter of all the ways the electrons could move. And so essentially you're just pretty much playing with it and seeing all the different places you could have a negative charge and how that would affect your double bond placement. So again, it was one of those things that was really weird to me, but if you guys practice it like once or twice, you can kind of get the hang of it. Does that sort of kind of make sense? So that's a valid question. What could he ask you about this? I mean, I haven't seen your test, but wink, wink, nudge, nudge. What he always asks is how many resonance structures does the cyclopentadiene anion. So that's what the name for this would be. So how many resonance structures does the cyclopentadiene anion have? And so you would have to then know that this equals this, and then be able to draw the resonance structures. Another way he can like show this to you or depict it, I guess, is by showing you. Actually, no, I lied. And then someone said, can we just count the sides of the molecule? In this case, that works, but I'm not sure that that will always work. So I'm going to say no. But yeah, that's mostly just because I've never tried it out, so I don't know if that works. And then do you know if this will be converted in the online lecture? Oh, if it's covered. Wow. I'm not 100% sure if it's covered in the online lectures because I haven't watched this chapter yet. But I do know that he does it every semester, so I assume he will at some point cover it. And then what does the circle in the middle mean? That is a very fair question. So essentially all this means is that the electrons are completely delocalized. That's why sometimes we see benzene looking like this, except less ugly. And so all that means is that the electrons are going all across the benzene ring all the time. And so when it looks like this, all it means is that it's completely delocalized, but there is a -1 charge. So a -1 charge would just mean that you have a lone pair of electrons. And then someone asked, so if it's AA or anti-aromatic or aromatic, it could have a circle? Yes. And that would just mean that it is completely delocalized. Usually when they draw a circle, it means that it's aromatic, but technically speaking, as long as it's fully delocalized, they could draw it and it could be used to trick you. So yes, either one could theoretically have a circle, but usually it indicates aromaticity. And then there was one other example that he draws like that I wanted to tell you guys about, but oh, right, okay. So the last thing I wanted to tell you guys was this doesn't usually pop up on this exam, but it always comes up on the final. So I'll just mention it now and then I'll mention it again. So these are the two resonance structures of benzene, right? And the only difference is that the double bond placement is flip-flopped. And so neither of these are the correct drawing of benzene. So if he asks you, like, which of the following is true about the resonance structures of benzene, neither of these are an accurate representation of benzene. This is the best representation of benzene. And I'm only mentioning it because this kind of drawing does pop up on the exam, and so it's helpful for you guys to just know this. So does anyone want me to repeat it, or you guys got it, or any questions? Someone said he didn't go over this much in lecture. I'm not sure if that means he won't go over it until, like, for this exam material, or he probably just covers it in chapter 15. All I know is that he always, at least will have one question where he draws it like this, and it gets people super confused. Cool. Okay, so it is 1:52. So if you guys have any questions, I'll stay on for a little bit. But if not, you're free to go. I hope you have a wonderful day and enjoy your weekend. You're very welcome.